There are newer technologies in earthquake engineering design that are developed in various countries, and we are also following some of them. The simple question is, what if my building is on rollers? So if my building is on rollers, the building may go left, right, but still nothing will happen. Because the general understanding of an earthquake is, suppose the bottom is fixed and the earth moves, and the building is likely to move slightly different from the earth movement, and the differential movement is what we call drift, which is allowed is not 4 times delta. That means because of this drift only, there are bending moment, shear forces, and then member forces. All this happen in a frame elements. But at the same time, suppose instead of fixing it, I make everything on roller or isolator as the case may be. The building is going to move left, right without any relative deformation between ground and top. It may not be zero, but it is not that big to create a stress level. So that is a concept of base isolation, wherein a fixed base building is likely to experience a deformation delta. Even if it is well designed, it is going to be not 4 times height. That is the way it is. But however, if I have the same building with in isolator, the building will move left, right. Only the isolator will experience the lateral deformation. So if I design the isolator for the kind of lateral deformation that is going to happen for in this building, so my structure is safe, and the and the motion, suppose assuming that you put an earthquake, the motion from bottom to top is varying. The low deformation at the first floor, slightly higher in the other floor, more highest in the top floor. But in case of isolated building, the motion of the building will be exactly equal from bottom to top. Theoretically, there will be some difference here and there, but theoretically, the deformation is same top to bottom. If the deformation is that is called rigid body motion. If the building is moving rigidly from left to right and right to left, there is no stress induced, because the deformation, if delta only introduces a bending moment of 12a by L cube, shear force of 12a by L cube, and bending moment of 6a by L square into delta. All that happens in a frame because of the delta only. If the delta is 0, theoretically, if the delta is 0, then there is no issue at all. So that is a concept of base isolation. You will be surprised to know that even as early as building there in Indonesia, because Indonesia, you know that they experience a lot of earthquake all the time. So they were able to construct this kind of building on basis related structural system. Same is the case in China also. China, you have a set of colony, as you can see here. All these colonies are in basis related building only. So this is an interesting thing that really happens. Even uh, a 7-story residential structure can be on base isolation, and such a structure cannot fail during an earthquake, and it is an assured thing. So this is what is called base isolation thing. We tried this kind of ball theory on a simple model of a single story building which is resting on balls. This is called roller. What you call roller? It will be like this. There are two spherical balls that are kept here, and there is a plinth beam and there is a wall. So this is a single story building that I kept in my shake table to understand whether the building in roller will perform better. So we are able to, this is a kind of construction. You put balls here, and then there is a base slab, and then there is a wall, and there is a building, and this is a building that we tested in our shake table. And you will be surprised to see that even though the earthquake has large deformation, none of them is transmitted to the first ground floor and first floor. I mean, at the base as well as top of the structural system. That this picture shows you that even though the displacement is as high as 8 mm peak, but we are getting only 0.1 mm, 0.2 mm like that because of various small things. So this is a simple demonstration at student level, not for practical purpose. Actually, this is done by some students who are doing PG with me. So it is just to prove that if your building is on balls, say rollers, obviously you are able to get the vibration filtered fully, and the building will have rigid body motion, no relative motion, nothing will happen. The building is very safe, and same is the case. Suppose assuming the uh, idea of a railway track on ballast. So suppose the right train, when it goes, there is a large vibration that is created in the soil, but because of the presence of ballast, it gets dissipated, and then you don't get the vibration. Of course, still we get some vibration near the building, near the track, you know that, but it is already filtered one. So yeah, keeping that idea in mind, so we created a tank, and in which ballast is filled, the building is built with ballast, and the foundation is embedded there. no rigid connection. Okay, no rigid connection. And then there is a G plus 1 building. So this is also, you can see the seismic test has proved that even though the deformation is nearly about 12 in the base, and we are getting only zero point 0.5 to zero point 0.6 in the first floor and second floor. So essentially, there is a kind of filtering that happens. So these are all just for demonstrative purpose. As a student has to understand the concept of vibration transmission in a building from earthquake by having these kind of simple ideas. So any of these innovative ideas, suppose if you bring that can be tested, so that we can introduce some new ideas or something like that. So the same thing we did in a shake table, because the issue is a soft story building. The soft story building, we already seen that it is very dangerous situation because of the large deformation that experience in the ground. So if I am keeping the building at the on isolator, obviously the isolator will experience heavy vibration, so that the building will not experience any vibration. So this is a concept in which this soft story also can be an on isolation kind of thing. So this is what we did, and as you can see here, the base, the earthquake has nearly 28 of vibration, which has reduced to the first floor to just 3 or something. As you can see here, 4 is the peak that we have ever got. That is, we are having a reduction between nearly 30 to 4 So 7 time reduction is possibility. So a soft story survives much better. So this is a curve that is for story 1, story 2, story 3, story 4, so all these 4 stories. Let me say level 1, level 2, level 3. So in all these level 3, the kind of vibration is very, 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 very less compared to the base vibration. Base vibration is nearly going to 30 which is finally you realize only 3 to 4 in one case, that is at 3 level. So what I am trying to say is, the vibration level can be drastically reduced, or of course ideally speaking you can make it zero, but there is no ideal, because there is always damping is there, and then there is the presence of so many structural things are there. So obviously, but only thing is you can reduce from 7-fold or 10-fold as the case may be. Obviously your structure is safe if you are reducing the vibration to 1/10 of what is ground is experiencing. So the structure will not fail at all. So this is the concept of base isolation that is possible even in soft story building. So rest of the idea that we had is passive energy dissipation devices. So it is like keeping a damper in a building. For example, if you have a car or any vehicle, so the vibration that is transmitted from the car to the road to car is arrested by some kind of damping devices inside. That is why the car, you feel very safe inside, and then it is not vibrating seriously. So that kind of idea, why don't we give in the building itself? So that is the way it is. So what we have is something called the PED device, that is passive energy dissipation device, which is based on X plate. This is developed by us. It is nothing but it's a 2 thick plate cut into X shape like this, what you see here, and then connected to 2 plates, 3 plates, depending upon the required design of requirement. And this is a product that is developed. If you connect this X plate in a frame system like this, suppose you have a frame system of 3-story building, and you connect, this is called chevron connecting brace. So you got connect, and the X plate is here. Suppose if you do like that, the energy all the energy, because this is the weakest link here, most of the energy of the lateral deformation will go here, and that may deform seriously. But your the experience of column and beam that is here will not experience that kind of vibration. Similarly, we have also developed on viscoelastic solid damper. So this is also patented product. So this is actually, suppose this is a steel plate that is on bending, and this is rubber on shear like that. So these are all some basic mechanics concept of a material that is intelligently used in the building. And this is also one more thing is lead extrusion damper. Suppose this is cylinder, inside we filled with lead, and there is a piston that goes up and down. In the friction, you get that damping that is happening there. So people also done the roof isolation because the roof. This is very similar to the AMVN concept, that is auxiliary mass vibration utilizer concept. Suppose the natural period of the building is say 6 seconds, and then you keep the top floor on isolator, whose natural period should be also 6 seconds. So most of the energy will flow there. Worst case, that may fail. Of course, it will not fail. I am just saying. So we can, if we can only take care of this as dynamically, otherwise it is a very safe system. In Armenia, they have done this kind of roof isolation system, and it is successful. Coming to olden people, buildings of 24 centuries old, you have monuments, all that. What they have done is they have large solid shear wall here and there, and the pillar size also is very large. So they have designed earthquake proof. For example, this is Parthenon of Athens. So earthquake proof by increasing the size, massive building. Let me say it is massive building or rigid building as the case may be. A flexible building experiences deformation. A rigid building experiences less deformation. That is the way it is. So if you put only a bale cube for any of the one of these columns, it will be huge because of course height is also large. That is one thing, but the moment of inertia also is large. That way it is, and the rigidity is, if you see the plan, there is a large thick wall that is all around. So this increase the lateral stiffness of the building. That is how they have taken care, in my opinion. So this is the data of that Pantheon, 44-meter height cylindrical drum. It's a tremendous mass. So this is a Pantheon that is there. That is, this is a circular building with a dome at the center. But this is also, suppose if there to be a lot lateral force, so there will be an uplifting here and there is a compression here, that kind of thing. So that they are done by skillful handling of lateral resistance system. It resists lateral force much better because top circular and in this section we have some kind of top uh, looks like a circular dome, but at the bottom it is a rectangular square as the case may be by arch section. So these are all the things that this is how they have taken care of lateral resistance system in those days. This is Gothic of Cathedral. And in the Gothic of Cathedral, for example, this piece which is vertical, it is very similar to a vertical member giving a priestess to this area, that kind of thing. So similarly here, so suppose if you see this as a horizontal element, that means there is a priestess that is available, pre-compression that is available. Here, for example, this pinnacle is nothing but the vertical. It looks good. That is one point of it. But in the buttress, it gives additional compression to the member so that this uplifting cannot happen due to lateral force. So this kind of interesting concept they have introduced in those days when modern technology was not there. So they are also equally good. To conclude, I would like to talk about Big Temple of Tanjore. Big Temple of Tanjore also is a serious problem because we have 80 ton of load at the top. Because normally, if you keep heavy load at the top, it is not okay for earthquake because Newton said fourth mass into acceleration is a force. 80 ton of mass into, let me say it is 0.2 g, means 80 into 0.2 is about 16 ton of lateral force to be there. Will this sustain 16 ton of force when it is applied like this during an earthquake? That is a big question. The answer is because this is a hollow structure with pyramidal nature, solid at the end and then inside hollow. So the area is suitably done. And then this 80 ton divided by that area is called some compressive stress. So there is a pre-compressive stress that in every layer, depending upon the area that is there, maybe slowly decreasing also. But if there is a lateral force that is going to, let me ask in my example, 80 ton in 0.2 g is about 60 ton. Suppose if you apply horizontally, there are, first is there is a friction between two elements, and also there is a pre-compression that exists on this element, which will save from this kind of lateral forces. Is what my guess of how they would have thought of for the lateral forces. So thank you.